I have pathways for the heat transfer. So heat storage. And disturbance. Well, this model made up of thermal resistances, insulators, some storage systems and more. So I have two states here, X1 and X2, which would be the voltages of C1 and C2, or the temperatures of my walls. Yes?
What are the two R's that don't have subscripts? Or that's just R?
This is R3, and that's just R0. Okay, you can get the state equations for this. I'm going to here. So this is, so the states are voltages. And I have two inputs, or well, two inputs combined into one vector here. And if you want to see what all these terms are, you can work this out. Those are a mess of parts. I have some desired states. I want X1 desired to be some constant. And I want desired state for X2. Let's say to be some constant. Value B1 to be.
Hey, quick question. question.
Yeah.
On A12, the last term in it, is that a D1?
Yes, and D one's defined here.
Gotcha. And then a D2 and A21, is that?
Yeah, those are Ds. These are D2s, D2s, D1s, D1s. That implies that our, since I want constants, that our A matrices for our inputs are 0. That makes sense? We're trying to do this type of idea. But I want it to be a constant. That says that x dot's going to be 0. Right? So A0. Easy way to define these inputs based on the dynamic system. In this case, it's trivial. All right, then I have our output, C1 to C2, and we have some controllers. We have 2 controllers, K1, K2. Well, our controller state matrix, same as we've done before. And I need the inverse of it. Let's just find the inverse of it. And it's of course really ugly. And, all right, 2 by 2 symbolic, they'll let you do that. Yeah, let's do it. This. And then I need to find C, A minus BK inverse B. Now I have all the parts to find this E prime. He is really ugly. It's ugly. Oh, that's I wish you had numbers, it's a lot easier to do this. I should pick a numerical, but what we're after here, once I define this speed time, I have to find my gains for my other task. All right, so remember the whole state equation is in terms of error. Looks like the following. This is our original setup. X. That's error. X knots. That's our meta state. Now, let's see what this whole thing ends up being in terms of block diagram. Make a little more sense. These are our desired states. Except by tracking things as analog, temperature 1, voltage V1, V1 bar, temperature of voltage 2, V2 bar. They go into summation each. Output of the summation is that this is going to be minus E1, and after this is going to be minus E2. Those are controller gates. How do we find the controller gates? Pole placements, and we've also. They get summed. Plus creates a U, which is here's our plant. Output X1, X2. One comes in here. X2, so X2 comes in here. There. X1 comes into there. So compare the state that I want with the state that I have, each one of these. And then I'm going to take, here's our disturbance. I don't want to affect on. It's going into some gain, some process. I can't do anything about that. But I can take these signals, go through what we call KR1. KR2. Counteract that. Okay. Those are the fun. So this guy, these are the gains that I'm going to try to, given my desired state, minimize the effects of this disturbance. That's just going to try to subtract them. That's what we do. kind of makes sense what we're doing here? So this part's what we've done before. This is basically straightforward control. What we've done is define these new gains here, so I can take my inputs and try to counteract this disturbance via P4 system. Yeah.
On your numerator here on B prime, the second term in the numerator, is it A sub 2?
Oh.
What's that?
That's, for this example, just go through the full formula example how to solve this exponent. Some books use other symbols here, so we use an X number sign up here, call it something else, whatever you want to call it, doesn't matter. All right. Questions on this? Is it making sense? A little bit. This is the most mathematically messy approach. Talk a little bit about pseudo inverses, I guess. Rough on those. Let's look at the idea of an inverse as the means of solving linear set equations. Linear set equations.